So hello everyone, this is lecture 14 for the solid state physics, and we were just completed in the last lecture the density of states. I have given you some homework, so we will discuss in this lecture first the solutions. First I gave you that proof for the 3D we get this expression for density of states. So I hope you tried, but if you are get stuck somewhere, then let me tell you that just like here we find the area of squares and divided the whole area, or we can call this the annular region by the one square area, and that gave us a number of squares, and that was the number of modes actually. Okay, likewise in 3D case we can assume these are as spheres, big spheres. So there will be some annular region between them. So there is this k plus dk and k radius will be there, and we'll get volumes. So as like there was squares, now we will divide the area with the cubes, because now we can calculate the volume by cubes. So each cube will give us, if there is large number of modes, then each cube will give us one mode. Okay, so we will divide just this annular region volume by one cube. And just like here we use psi xy, now we will use psi xyz, and we will get e to the power I kxx, I kyy, and e to the power I kyz. And when we solve them separately, we will get the same expression for all the three: 2n pi by l, 2n pi by l, 2n pi by l. And what this length give us? This give us the difference between k of each mode. So that will be remain same in 3D case also. When it is upside and downside, then that difference will also be 2 pi by l. So we'll get cubes of side 2 pi by l. So what will be? Just volume of the biggest sphere will be 4 upon 3 pi k plus dk cube minus volume of this inner sphere 4 upon 3 pi k cube, and that volume difference will be divided by volume of one cube, that is 2 pi by l whole cube, it is side cube. So we'll do this just like this. When we let me focus. So we'll subtract this and divide by this one cubical volume, and we will get total number of modes. So when we subtract this from this, we will get something like this, and it will cancel out. Inside dk cube is very small, dk square will neglected, then this term will remain. So 3 will cancel out, we will get 4 pi k square dk, and in the denominator it was 2 pi by l cube, so it will become l by 2 pi cube. So here your expression is here like the same, l by 2 pi cube 4 pi k square dk, that will be gk tk. Gk tk give us number of modes in 3D. So that's how you will get this. Now I gave you some problems. Now you can solve them. Just you solve in the 1D case. Just you have to remember that you need to use this formula for 3D. Just find the dk value with the relations, as we know in the non-relativistic case the electron was, the energy term was this. So we can just relate k with E, and we can find dk in terms of E, and just substitute in this equation, and we will get the density. Means when we get the modes, then divide by that dE will give us density of states. Okay, and same for the relativistic case, just as we did here. From here you can get the expressions. Those were for relativistic case energy by h cut kc, and for photons frequency was in terms of k was this. So here you can find the dk term and k also, and just like phonons you can get from here, and for the magnons you can get this from here. Or just finding the four expression, you can use this. And if you just want a relation or you want a plot, then you can use these tricks. For electron, the density of states will always multiply with 2, and the spin degeneracy, that's 2 because spin degeneracy, and 2 multiply what? 2 multiply this term, whatever you get. For one dimension this, 2 dimension this, 3 dimension this. Okay, so we can just I gave you one example, then you can just try that. For non-relativistic case, we can see that E is proportional to k to the power 2. So from here we can see k to the power 2, then s will be 2, and dimension is 3 because we using in 3 dimension. So we will use 3 by 2 minus 1, then it will came out to be 1 by 2. So if you solve all the equation, in the last you will get rho is proportional to e to the power 1 by 2. Okay, so that's how you can calculate for any of them. If it is in the omega terms, then you can use this. If it's in the energy terms, you can use this. You can directly find the relation and plot. But if you need to find the number of states, then that for that expression you have to solve these equations. Okay, I hope you get the idea. Now today we will start a new topic. Not that's new, but it is new here. So it is lattice vibrations. So we will talk about the lattice vibrations. What are lattice vibrations? Well, what we will study in this topic first, let me tell you. That is lattice vibration of 1D monoatomic lattice, lattice vibration of 1D diatomic lattice, and in this the diatomic lattice we will have the acoustic branch and the optical branch. Third, we will study about the modes of vibrations in 1D, 2D, and 3D. And the last, we will also study the concept of phonons. Okay, so what is this thing? In this 1D monatomic lattice, we will study that if there is this atoms in a 1D dimension and they are vibrating and they are monoatomic, means they are just single atoms of any metal, it can be possible. Okay, so their vibration we will study. And then if it is diatomic, means oxygen is not, it's gas. If we find something which is diatomic, and then we will study the vibration of those, means there are two atoms in a molecule, we are studying that. So we will study that, and then we will study those vibrations, their modes in 1D, 2D, and 3D cases. Then concept of phonon. So you will understand this in the coming lectures. Just don't get stressed. It's easy. We will start from very basic. So we are studying here solid state physics, so it's all about solid. So in introduction, let's say, what are waves? What are waves? So waves are nothing but disturbance in a medium which distributes energy from one location to another to other. Okay, so just like you throw a stone inside a river, then you will see that disturbance is created in that medium. And now what happens, this disturb will distribute throughout the lake or river, whatever it is. So it will just distribute the disturbance from one location to another. Then that thing is called waves. Okay, in solid if we discuss, then in the solid these atoms are very uh, means they are together very tightly as compared to liquid and gas. That's why we call liquid and gas as fluids and solids are not fluids. So here their interaction, they have very low viscosity, means they can't even move. So but still they can vibrate, we call assume or imagine this bonding between the atoms or the molecules inside a solid like a spring. Means it's not exactly a spring, we just considering it like a spring. Okay, because it has this property of elasticity, means if you just pull some atom, then it will just vibrate and it will turns to its original position. So that's why we are just taking this spring thing example. So it's like we stretch this box out, then we will release it, then it will just vibrate. So that's how the solid and the waves inside a solid also works. If you just take some atom or disturb some atom inside a solid, that will just vibrate and it will disturb the others also, and that form the waves inside a solid. Okay, so those waves are nothing but elastic waves inside a solid, and quanta of elastic waves is called phonon. Quanta of those elastic waves which are produced inside a solid. So those energy, the minimum energy, means you need to just multiply them and you can give any energy inside a solid of waves, then that quanta of elastic wave is called phonon. Okay, hope you get this idea. It's just an elastic wave inside it. So atoms in solid can vibrate because of why how it is possible to make atoms in a solid vibrate. So those can vibrate through different type of energies. That is it can be internal energy of the system. Okay, And it's possible from the external energy also, means either they will be vibrating by their own because of some internal energy, or you are just applying something from the outside. That's how they can vibrate. So in the outside, we can how we can apply some energy. It can be in the form of mechanical, or it can be in the form of electromagnetic waves. Okay, so those applicability of external force or energy will lead to different types of property of the solid. Means if you applying some mechanical energy on the solid or the system, then it will change its thermal properties. Like if you are hammering or just increasing temperature or something, then thermal properties of solid, what are the thermal properties of solid? That's nothing but the heat conductivity, specific heat and all. So those properties of a solid or a material will affect if you apply mechanical energy on a solid. But it is possible to make them vibrate by EM waves also. And then we see that that will affect the optical properties of the solid. Optical properties of the solid. And what are the optical properties? These are nothing but reflections, refraction, refractive index. They will be affected if you apply EM wave and they start oscillating inside the solid. So these will be affected. If you get the idea of these vibrations, you will know more that how it's happening. Just we are getting one step closer. Okay, first we will discuss about the lattice vibrations of monoatomic lattice. Monoatomic means there is a single atoms. Okay, means all the metal or the solid is form of individual atoms of same properties. Okay, so let's say there is these atoms of each of mass m, each of mass m. Okay, so it is just a equilibrium state now, equilibrium state. Now we just applied some energy, or you can say mechanical energy, anything. It can be EM or mechanical, anything it can be. So we just applied some force or something, so this system get disturbed. The system get disturbed. We applied the force in this direction, so the system will disturb like this. Means this atom will reach here, then it will also displace here, it will also displace, it will also displace, but the displacement will be different. Means if you are applying a force this side, then this displacement will be more, this is less, this is more less, this is all less. Means that's how the displacement will go. This is nothing but a snapshot at a particular time. Means if you take the snapshot of this system in the displacement mode at a particular time, then you will see this situation. It's a particular at a time situation. Means if you just see the whole case, it will just vibrating. Okay, so you can see that how it is. So this distance between each atom was a. Now we introduce this u term, and this is nothing but it is showing us the displacement from its original position. So first it was here, now it is displaced by un plus 2. Second atom is displaced by un plus 1. Third is un, and fourth is un minus 1. That's how gonna go. Now if we see, if we look at a particular pair, like we can look this pair, when it is get stretched, then we will see that this length gonna stretch, this will be stretched, then we will see that both atoms gonna come to their original positions. So for this atom the force will be in this direction, and for this atom the force will be in this direction. That's how. And same from here, same in the all cases, all gonna come to their original positions. Force will be like this. Okay, so if we just consider the term a beta, first it is like un plus 1 is greater than un. This is, you know, this is greater, this is less, this is more or less, this is more or less. Okay, so just consider this particular single atom will be generalized. Then this atom, when this stretching is going on, then it will feel feeling this force in this direction. I just told you how this force in this direction, because when you expand this, they all want to come together. Okay, means this string is stretched, then they will come together. So this force in direction, and we see that displacement is also happening in this direction, and this displacement is nothing but un plus 1 minus un. Displacement is this, and this is greater, this is lesser. So we see that force and displacement are in both directions. So the force we studied for the spring, that is F equal to minus kx. That is because that was because if you stretch this, then displacement, the force is in this direction, the restoring force is in this direction, but the displacement is in this direction. That's why we take the force equal to minus kx. But here we see that restoring force is in this direction and displacement is also in this direction. The force will be this displacement into beta. Beta is nothing but force constant, or we can say spring constant. Like we have the spring constant, that's same we have force constant here, we call it beta. And on the same particle we can see that there is this force also. And how much is this force? Now we see that displacement is in this direction and force is in this direction, so the displacement is u1 minus u1 minus 1, and force is in this direction, f2, so it will be f2 equal to minus beta this. Hope you get this point. Now total force in this particle, this u1 particle, means n particle, will be f1 plus f2. So total force in this particle will be beta un plus 1 minus 2 mu n. So un minus 1, we just added these. Okay, now force can be written in this form, d square un by dt square. Un is nothing but displacement, so that will give us the acceleration. So ma equal to beta this term. So this is nothing but equation of motion of this particle, the n particle. That's why we were doing all of this, because the motive of us, or our motive was to find the equation of motion for n particle. Now we will end here today. We'll discuss more in the next lecture. Just have a better understanding of this by seeing the previous lectures, and just see whatever, or the listen whatever I told you today again. If you having still any doubt, you can join my Telegram channel, and there I also introduce the Telegram group where you can just chat with me or your friends. Okay, so you can ask any doubt from anywhere, you can reach me. So thank you. Just share this lecture to more and more people. Thank you again.